Hi everyone, in this example we're going to work on looking at a graph of a function and talk about all sorts of different things. Okay, so first just how do we evaluate a function represented by a graph, and that's what this list over here is asking for. So for example, if I would like to find m of 1, I am looking for my x value to be 1, x is our inputs, and I look at where I hit the graph. I hit the graph right here, so it looks like my y value, which is what this is asking for, is -1. So m of 1 is -1. M of 2, so we go to where x is 2. Right here on the x-axis, we're hitting the graph, so m of 2 is 0. My y value is 0, and my x value on this graph is 2. So basically the way graph represents input outputs pairs is by points on the graph. So a point on the graph pairs an input and an output according to that function. M of 3 is kind of an interesting one because there's a couple of options, but the open circle means there actually is not a point sitting at 2, 2. So we're going to choose, 3, 2. We're going to choose 3, 1. And then last one, m of 4, there aren't two choices, there's only one, and it's an open circle, which means m of 4 is undefined. Okay, we could also ask for something like this, m of 7 minus m of 5 over 2. And we can calculate that. M of 7 is 2. M of 5 is -2. So 2 minus -2 over 2. So this becomes a 2 plus 2, which is 4 over 2, which is just a 2, so that ends up having a lot of 2's involved. But more important than being able to do that calculation, I hope that when you see this, you recognize that you've just calculated an average rate of change. So basically, we took this point, and if you connected the dots between those 2 points with a straight line, it doesn't perfectly match up with the curve, but it's pretty darn close. So this is a little curve. It'll deck down below and then up above a little bit, the line. But this is estimating the steepness of the curve between these 2 points. And you should recognize that as soon as you see this. I'm taking a y value minus a y value. Function notation is cool because you can see right in here that the x values you were supposed to use were 7 and 5, and it happens to be true that 7 minus 5 will give us the 2, so this really is a rise over a run. M of -0.5 over -0.5. Okay, so m of -0.5 appears to be about 2. So this is 2 over -0.5. So I've written that as a decimal, but I actually think I would look at this and say, okay, that's 2 divided by -1/2. To divide by a fraction, you should multiply by its reciprocal. So it looks like we're getting a -4. Again, this one's, I think, slightly trickier, but you can interpret that as a slope if you think about this as, what if I had m of -0.5 minus 0 minus 0? It's the slope between, here, let me grab another color so you can see this a little better, these 2 points. So -0.5, m of -0.5, and 0, 0. If you draw the line between those two, we've just calculated the slope of that line. So a little more hidden, but basically, if we take m of something, we're talking about a y value, which is a vertical distance, so that's a length. If we divide a length by a length, it can get a little weird, but one of the possible interpretations of what we get when we divide a length by a length is slope. So if we divide a vertical length by the appropriate horizontal length, we're talking about a slope. Okay, let's see. Some composition. Oh, I meant to sneak some inverses in here. I think I will. Let me not forget. Let's try m inverse. Oh, I didn't sneak an inverse in here because this function isn't 1-to-1. Okay, never mind. M of 7. All right, so if we look for m of 7, whenever you have all this composition, you always start from the inside and work your way out. So first this one, m of 7 is 2. So get rid of that and we say, okay, now 2. Next, we want to plug the 2 into m again. So this 2 is no longer our y value. Now we're thinking of this 2 as our x value. And when we plug in 2, we get 0. So now we're done with all of this. and then we're supposed to take that 0 and plug it into m again. When we plug 0 into m, we actually get a 0 back. Okay, so there's that one. So composition inverses are going to be mixed in here as well. We don't want to have forgotten about those. We'll do both of those things with trig functions, so just being good with the notation is helpful. The next one is similar, but we have to do it 4 times, so we're starting at 8. If we plug 8 in, we get back 3. So this is m of 3. When we plug that 3 back in, we get a 1. So now we're done with all of this. And we're plugging 1 into m. When we plug 1 into m, we get -1. So now we're done with all of this. And then last thing, plug -1 back into m one more time, and it looks like we get out 4. So you can compose as many times as you want to. You just want to make sure that you are always taking whatever it is you're plugging in and thinking about it as an x value, and then you get back a y. However, if you plug that y back into something else, it becomes an x value again. Okay, last couple here are some solves. So we should be able to solve m of x equals whatever I give you, and what I'm hoping is that when you look at that, you recognize that m of x is y. So this is saying, tell me when y is equal to 2. So if I look, here's y equals 2. I hit the graph right here. The whole doesn't count. There's not a point there, but I do hit the graph right here as well. So it looks like m of x equals 2 if x is equal to -1/2 or 7. Okay, so 2 possibilities, and that's completely fine with functions. The rule is one input should only have one output, but there is no rule that says that an output has to go back to only one input. You can have an output that comes from more than one input. M of x equals -3. Okay, so we're looking way down here, and we don't actually ever hit that horizontal line y equals -3. So I would say this has no solution. And in terms of deciding when you should say undefined versus no solution, it actually shouldn't be too tricky if what you started with was solving an equation. It already had equality in here, and you were trying to find the x that makes that true. Solving is when you would say no solution. I was trying to solve, I couldn't do it, there's no solution. Whereas here, you're not solving any equations, you're just plugging a number into a function and you're trying to get an output. And what you're saying here is the function is not defined for an input of 4. Another way to say this one would be not in the domain, if you like that better, not in the domain of m. Okay, so that's the first chunk. There is a little bit more to this one. Let me grab another paper here. There's also some transformations review I'd like to cover here. Ignore the little colored dots. They're not showing up when I actually look at this in Word, but they continue to show up no matter what I do when I print this. So sorry for those. They're not supposed to be there. Okay, so this is a little bit of transformations review. Up at the top, we have a graph of the function y equals m of x. And now we're being asked to sketch a graph of the function y equals m of 2x plus 2. So the m should jump out right away as telling you which function you're starting with. This guy right here is my starting function. It's a messy one. This one's kind of a lot of work. I don't think I gave you one this messy on your homework. We'll have to follow a bunch of points. And then we're multiplying our x's by 2 and adding 2 to them, which looks like multiply x by 2. Remember, x's work backwards, so this is actually horizontal compression. You're going to cut all the x values from the original function in half. And then plus 2 looks like left 2, but it's actually not. There's a little bit of trickiness here, and however you deal with this is fine. Different teachers do this different ways. I do it by factoring. Another choice would be to reverse orders. So my rule is I always do my shifting last. If you want to follow that rule, then you're going to need to factor in order to get your shift right. The reason I like to do that shift last thing is so that I'm always stretching, compressing everything else away from the axis and not away from some other value. Okay, so I'm going to do horizontal compression by 2, and I'm going to shift left by only 1. So let's see if we can follow some points here. Horizontal compression by 2 cuts your x value in half. So this point is negative 3, 8. It would end up at negative 1.5, 8. And then if I shift left, it'll be almost back where it started. It'll be at negative 2.5, 8. This point, and you can kind of pick and choose what you think are important points, but this one would compress to negative 1/2, and then it would shift to negative 1.5, and the y values aren't going to change for any of these points. We're only transforming x's, so that'll stay negative 1.5, 4. 0, 0, the compression doesn't move that point, but it will shift left. So it'll be at negative 1, 0. The bottom, that's definitely a good one. You probably didn't have to follow every single nice point in between here, but this is a really good point to follow. So 1, negative 1, compression will put it at 1/2, negative 1, and then shift will put it at negative 1/2, negative 1. We could follow this one, but I think I might just skip up. Well, here it's easy. If we compress, it goes from x equals 2 to x equals 1. And then if we shift over, x equals 0. The open circle was at 3, 2, so it will end up at 1.5, 2 when we cut the x in half, and then 1/2, 2 when we move left. So an open circle at 1/2, 2. There should then be a closed circle directly under it. Again, the y values aren't changing, so this had the same x coordinate, x equals 3. It should get cut in half and then move over. So there's also a closed circle right below that. Let's see, this one is at x equals 4. So we cut that in half. It goes to x equals 2, and then left to x equals 1. The bottom is at x equals 5. So if we cut it in half, it's 2.5. And then we move over, it's 1.5, negative 2. Okay, almost done. This one is at 6, 0. So if we cut in half, it'll go to 3, 0, and then we move left, it'll be at 2, 0. And then 7, 2 will go to 3.5, 2, and then 2.5, 2. And then I guess we can follow this very last one, 8, 3, cut in half will go to 4, 3, and then we move over, it will go to 3, 3. 3, 3, and that's where my arrow is. Okay, so I followed tons and tons of points there. Again, if you can just snag a fewer points and still get the basic shape looking pretty nice, I'm okay with that. But those were all good points to follow. Otherwise, it should still look related to this function we started with. I made it skinnier, so things are going to be a little bit exaggerated. Let's see if we can make that show up. And then this, it's going to curve down, and then back up, and out to here, and there we go. Okay, so there it is, horizontally compressed by 1/2 and shifted to the left 1. I'd also like to fold here, do one more. So those were both horizontal transformations. Let's make sure we look at some vertical transformations as well. Okay, so this one wants us to sketch y equals negative 2 times m of x plus 1. So similar, but now instead of the transformations being in the parentheses, everything is outside. So these will all be affecting your y values. They happen to the output of function m. So this is a horizontal flip, multiplying by a negative. We'll flip the graph upside down. This is a vertical stretch. Unlike the x's, the y's don't do things backwards. And this is a shift up 1. So that's my transformation list. I'm starting with the same basic function. Okay, so let's see. If we look at points, say we look at negative, what is this one? Negative 3, 8. When we flip upside down, it would be negative 3, negative 8, and then we double our y. So it would go negative 3, negative 16. And then up 1, negative 3, negative 15. That's going to be off my grid here, so I'll just leave that one off. But we know negative 3, it's way down here somewhere. So let's go ahead and try negative 1, 4. Okay, so when we flip upside down, we land at -1, -4, and then we double our y, -4, -8, and then we shift up 1, -4, -7. I think I just said that wrong. It is -7. -1, -7. Okay, sorry guys. The 0, 0 point, that one's actually kind of nice because the flip won't move it. The vertical stretch by 2 won't move it. When you vertically stretch, it's away from the axis, so points on the axis actually stick. The only thing that moves it is the shift up 1, so it'll go through 0, 1. The bottom is at 1, -1, so we flip, it's at 1, 1, we double it, lands at 1, 2, and we shift up 1, lands at 1, 3. Okay, this one again, if you want to follow every single one, 2, 0, the flip won't move that point, and the vertical stretch won't move that point. Shift up 1 will, so it'll be at 2, 1. All right, 1, 2, 3, 2. Flip will put the open circle at 3, -2. Stretch will put it at 3, -4. And shift up, we'll put it at 3, -3. So open circle at 3, -3. And then close circle, 3, 1. When we flip, will be 3, -1. And then we do double our y value, vertical stretch, so 3, -2. And then we shift up, so 3, -1. Right here is our closed circle. Okay, the hole, again, the flip and the stretch won't affect it, but the shift up will. It will land at 4, 1. Okay, and then the bottom is at 5, -2, so flip puts it at 5, 2, stretch puts it at 5, 4, shift up puts it at 5, 6. Oh wait, I'm sorry, 5, 5. I can keep track. Too many points. 4, 5. Okay, this one again, flip and stretch won't affect, but shifting up will land us at 6, 1. And then 7, 2, when we flip will land at -2. When we double it'll land at -4. When we shift up 1 it'll be back to -3, so 7, -3. And then last one, it looks like it hits 8, 3. So when we flip it would be 8, -3. Double it would be 8, -6. And shift up it would be 8, -5. Okay, so we're now headed out the bottom. And then we come up through this point. And down and hit the open circle. Okay, so again, we followed lots of points, but you want to keep track of this. So we flipped it upside down. We've stretched it out so it's taller. And then we've slid the whole graph up 1. So we should still see this branch on the upside down. And then this one is going to come through like this. And then go up. And come back down. And there it is. Okay, so we should be able to do transformations. Again, I think I was a little nicer to you. I didn't give you quite such messy graphs so that you have to follow so many points, but we should be able to spot these transformations and apply them. Just flip back to this guy. Oh, I did. I forgot the other open circle. Okay, so right here should